Well, welcome to video number 11. Today we are going to talk about 5 applications of limits, derivatives, and integrals. And don't worry, that may seem like a lot, but a lot of these are actually pretty easy. So our first application is average value. To find the average value of a function over an interval, integrate the function over that interval and divide by the length of the interval. So in mathematical terms, that means if you're trying to find the average value of f of x over the interval a comma b, then the average value is the definite integral from a to b of f of x dx divided by b minus a. All right, so here's an example problem. Find the average value of sine of x over the interval 0, comma pi over 2. So what you do is simply plug in the values into the formula. A is 0 and b is pi over 2. So first of all, the integral of sine of x dx is negative cosine of x, and you evaluate that from 0 to pi over 2. So negative cosine of pi over 2 minus negative cosine of 0. And then minus negative is just plus. All right, and then the denominator is just pi over 2. And then cosine of pi over 2 is 0, and cosine of 0 is 1. So the final answer we'll get is 2 over pi. So average value is pretty straightforward, and that's all there is to it. So the next application is graphing. So the red line represents f of x, and you're told to graph f prime of x. So how can you do that? Well, some key points are, so the most important thing is that you remember that the derivative means the slope at a point, and at vertexes, the derivative is 0. So let's go ahead and graph the derivative. On the left side of the graph, you'll see that the function is decreasing and the tangent line is very steep. So that means that the derivative at the beginning is very low. And then you'll see that the tangent line gets less and less steep. And then eventually at the vertex right over here, the derivative becomes 0. And then after that, the function begins increasing. All right, so the derivative becomes positive, and then the derivative increases further and further until about this point right over here. And then after that, the derivative starts to decrease. So like right over here, the tangent line, you'll see it's not as steep as this one. And then at the vertex, the derivative is once again 0. And then the function begins to decrease. And then the derivative decreases further and further. You'll see the line gets steeper, and then the derivative begins to increase once again. So you see that this line right over here is not as steep. All right, and at the vertex, it's 0. The derivative is 0. And then after that, it just keeps on increasing, and the derivative just keeps on increasing because the slope of the tangent line becomes higher and higher. Okay, so let's go ahead and graph the derivative. So I'm going to change colors. At the beginning, we know the derivative is very low. All right, so let's start right over here, and then it gets higher and higher. We know that. And at this vertex right over here, the derivative is 0. All right, and then the function begins to increase. So the derivative goes in the positive direction now. And then at approximately this point, the derivative starts to decrease. And at this vertex right over here, it's once again 0. And then the function starts to decrease. All right. And then at about this point, we've reached the lowest point. All right. And then the derivative begins to increase again. At this vertex, it's once again 0. And then after that, the function keeps on increasing and the derivative also keeps on increasing. All right, so we've graphed the function. We've graphed the derivative of the function. So I'm going to go ahead and erase all of these black lines because we don't need them anymore. All right, so this blue line right over here is the graph of the derivative. And we can check that it's correct because notice that the red line is a quartic because we have 3 vertexes. And then that means that we know that the derivative of a quartic is a cubic. And that checks out. We see that this blue line right over here is indeed a graph of a cubic because we have two vertexes. All right, so moving on. So in general, for a polynomial of degree n, the graph of the derivative will be of degree n minus 1. All right, now if you want to go ahead and try this problem, then pause the video here. But anyway, here is the solution. Okay, so here, all right, so at the beginning, we see that the function is increasing, but the slope of the tangent line isn't that high. All right, and then afterwards, it gets higher and higher. You see this line gets steeper and steeper. And then at approximately this point is where it's the steepest. And after that, the derivative starts to decrease because the slope of the tangent line decreases. You see this line isn't as steep as this one. All right, and then it just decreases further and further. All right, so now let's try to graph the derivative. So at the beginning, the derivative is positive, but not that high. And then it increases until we get to this point right over here. And then it begins to decrease, but the entire time it stays positive. All right, and now I'm going to erase all these black lines. So we've graphed the derivative of the green line. So moving on now to related rates. So here's an example problem. Air is being pumped into a spherical balloon at a rate of 5 cubic centimeters per minute. Determine the rate at which the radius of the balloon is increasing when the diameter of the balloon is 20 centimeters. So that brings us into what related rates are. Finding the rate at which something changes by relating it to other quantities whose rates of change are known. So we know the rate at which air is being pumped in, and we need to determine the rate at which the radius is increasing when the diameter is 20 centimeters. So the general method for solving these problems is to define two functions, one of a quantity that you know the rate of change and one that you don't know the rate of change, and find an equation that relates the two functions, differentiate both sides of the equation, plug in the values you know, and solve for the value you need to find. So for this example problem, we can define two functions, the volume and the radius. So x represents time, v of x represents the volume at time x, r of x represents the radius at time x, and we know that v prime of x is equal to 5 for all values of x, and we need to find r prime of x at d equals 20 centimeters. All right, so we know that the formula for the volume of a sphere is 4/3 pi r cubed. All right, so we can form this equation right over here. And using implicit differentiation, if you remember that. So to differentiate this, you use the chain rule. The inside function is r of x, the outside function is x cubed. But anyway, you're going to get this. And the diameter of the sphere at the moment we know is 20 centimeters, which means the radius is 10 centimeters. And that means that r of x is 10 because we know that r of x is just radius as a function of time. And v prime of x, we know that's 5, so we plug those in. And then solving, you'll get that r prime of x is equal to 1/80 pi. And if you want units, it's centimeters per minute. All right, so now knowing this, here's a practice problem. If you want to try it, then pause the video right over here. And here is the solution. So you can find the distance between Abby and Bob as a function of time and find the derivative at x equals 10 seconds. So x represents time. So we have this function right over here, and we know this holds because of the Pythagorean theorem. And you might be wondering, shouldn't there be two functions? Well, the second function is just 2x. It's the function, it's the distance that Abby has walked as a function of time. I just didn't list it here. I just listed it immediately as 2x, but that's the other function. So we need to solve for f prime of x at x equals 10 seconds. All right, so differentiating both sides of the equation using implicit differentiation, you'll get this right over here. And then plugging in 10 for x, And solving, you'll get f prime of 10 is 80 over 2 times the square root of 2,900, and that is approximately 0.743. And then units would be meters per second. All right, so now we're moving into concavity. So concavity is commonly used in physics. It can determine how a lens reflects light. So a concave lens, so if light comes from this direction right over here, then it would mean that the lights converge to the left of the lens. And a convex lens would reflect light such that it converges to the right of the lens. All right, so similarly in calculus, a graph can either be concave up or concave down. And to determine whether a graph is concave up or down, take the derivative of the function twice. In the intervals where the result is negative, the graph is concave down. In the intervals where the result is positive, the graph is concave up. And why is this true? Well, notice that for concave up graphs, the derivative is increasing, and for concave down graphs, the derivative is decreasing. So we take the derivative the first time because we're dealing with the derivative of the function, and then the second time because we want to know whether it's increasing or decreasing. And then if it's positive, that means it's increasing, and if it's negative, that means it's decreasing. All right, so here's an example problem. Determine the concavity of the graph. So we just graph the derivative of this function. All right, so we've seen earlier how to do this. So this is a cubic. So the graph of the derivative should be a quadratic. And keep in mind the vertexes. At those points, the derivative should be equal to 0. All right, and then we take the derivative of again. So I'm going to change colors. And then the derivative of a quadratic is just a linear. So it's a straight line that looks something like this. All right. And now, so whenever we have something negative, it's concave down. And whenever we have something positive, it's concave up. So this is the point where it changes from positive to negative. So this interval right over here is concave down. And this interval right over here is concave up. All right, so this is how you determine concavity of a graph. And if you know how to graph a function, then it's very simple. All right, so now the last thing is local linearity. Local linearity can be used to approximate values. So for example, approximate the value of the square root of 4.5. Well, you can use the graph of y equals the square root of x to approximate the square root of 4.5. You know that 4, 2 is a point on the graph because the square root of 4 is equal to 2. And the slope at the point 4, 2, you just use derivatives. So the derivative of the square root of x is 1 over 2 times the square root of x. And if you plug in x equals 4, you'll get that the slope at the point is 1 over 4. So here's a graph of y equals the square root of x and the graph of the tangent line. If you could determine the y coordinate when x equals 4.5 on the blue graph, all right, so that's this coordinate right over here, then you've approximated the square root of 4.5. So how could you do that? Well, the first thing is you need to determine the equation of the tangent line. The general equation of a tangent line is y minus y1 equals m times x minus x1. And y1 and x1 are the point where the tangent line goes through. So in this case, this would be 4 and this would be 2. And then m is the slope. We know that's 1/4. All right, so we get this right over here is the equation of the tangent line. And if you plug in x equals 4.5, you can solve and get that y is equal to 2.125. So that is our approximation. And if you use a calculator, you'll get that the square root of 4.5 is approximately 2.12132. So our approximation was pretty close. We got it correct all the way to the hundredths place. All right, so now knowing that, if you want to give this problem a try, then pause the video. So this problem is actually a problem from a previous AP Calculus AB exam. Okay, so what you do basically is g of 1/2 just means this function right over here evaluated at x equals 1/2, and g prime of 1/2 means the derivative of this function evaluated at 1/2. So if you plug in 1/2 to 4x plus 1, you'll get that g of 1/2 is equal to 3. And then g prime of 1/2, you take the derivative of 4x plus 1, which is 4. And it turns out that since there's no x here, it doesn't matter that you're evaluating at x equals 1/2. G prime of 1/2 is equal to 4. So adding these two together, you'll get 3 plus 4, which is 7. And that's D. All right, here's another practice problem. And here is the answer. So the key points is first f of 2 is equal to 1. That's pretty self-explanatory. And f prime of 2 equals 4. That means that 4 is the slope of the line tangent to the graph of f at x equals 2. And that's important because we need to use the line tangent to the graph of f at x equals 2. And we need to know the slope of that. So we found out that that's 4. So here's the solution. We go from x equals 2 to x equals 1.9 because we're approximating f of 1.9. And so we have a change of negative 0.1. So our y undergoes a change of negative 0.1 times 4, which is the slope, and that's equal to negative 0.14. So our y changed by negative 0.14. That means the final y value is 1, which is f of 2 plus negative 0.4, and that's 0.6, which is B. All right, so here's a summary of everything today. So average value, so you just use this formula. Graphing, so these are the key points. The derivative means the slope at a point. At vertexes, the derivative is 0. And for a polynomial of degree n, the graph of the derivative will be of degree n minus 1. Related rates, what they are is finding the rate at which something changes by relating it to other quantities whose rates of change are known. So how you solve it, define two functions, and then find an equation that relates the two functions, differentiate both sides of the equation. So then you would have, instead of having the function, you'll have the rate at which the function changes, and then plug in the values you know and solve for the value you need to find. And so I put a link to more practice with related rates in the description, and you can go ahead and check that out. Concavity, just take the derivative of the function twice. Whenever the result is negative, it's concave down, and positive means concave up. And local linearity, if you have two values P and Q, where P and Q are close to each other, then you can approximate f of P by using f of Q and the tangent line of f of x at x equals Q. All right, so that's it. So that's the end of video 11. So stay tuned. There's only one video left. You're almost done with AP Calculus AB.